These in class, the ones that were assigned, but I actually want to talk about some of the ones that weren't assigned, just so you have an idea. So these are the projectile and kinematics challenges. So for number one, this is a velocity versus time curve. Notice it starts below zero, it's going more below zero, then it's staying at constant negative, then it's increasing to zero, and then increasing above zero. So it's saying at what times, if any, did the object have a positive acceleration and a negative velocity. So positive acceleration means a positive slope. Negative velocity means this is below zero. So I would say somewhere between here around 4.5 seconds and 7.25 seconds. So you need to know what you need to look for on a velocity time graph. At what times, if any, did the object have negative acceleration and positive velocity? So that means a negative slope, but above zero. That didn't happen at any of those cases. What times is the acceleration zero? It's when this line is flat, so from around 1.5 to 4.5 seconds. At what times, if any, was the object speeding up? It's actually speeding up anytime it's going away from zero. So you need to be careful. This looks like you would think it's slowing down, but it's going from like negative 1 to somewhere around negative 5 meters per second. So from 0 to about 1.5 seconds, it's speeding up. Slowing down here because you're getting closer to 0. And then anytime after 7.25 seconds, it's speeding up also. What times is the object slowing down? That's going to be between about 4.5 and 7.25 seconds. So it's getting closer to 0. What times did the object sit still for an extended period of time? There weren't any. The only time the object was still was when it was changing directions here at around 7.25 seconds. So this one was asking the horizontal distance traveled. So a key thing to think of here is if these all have the same horizontal speed, which they do, then the greater horizontal distance is going to be when the object is in the air for more time. So since they have the same horizontal speed, and this is a greater velocity upward because it's a steeper angle, it's going to be in the air for more time. So these two would be in the air for the longest, and therefore they go the farthest. These two, C and D, would be in the air the next longest amount of time, and these would be in the air the shortest amount of time. So this is sneaky with things, and the explanation's down there. Rank these rocks greatest to least in terms of the heights they reach. They're all launched at ground level, same angle, different masses. So the mass doesn't matter. The speed does matter. So the greater the speed that it's launched, the greater the maximum height. So 8, 8, 8, so that's CDF, then BG, then AH, and then E. Mass doesn't matter, because the rate of change for all the vertical velocities would be 9.8 meters per second every second. For number 4, acceleration at the top. Well, as soon as this leaves the cannon, we're going to assume that the object's acting like a projectile, so there's no acceleration other than gravity. Gravity still acts on the cannonballs at the top of their paths, so they would all be accelerating at around 10 meters per second squared. Horizontal speed at the top. So the vertical speed at the top of these would all be 0. The horizontal speed depends on the angle, and it said those were the same, and the launch speed. So again, the ones with a greater launch speed would have a greater horizontal speed, and that does not change during the path of a projectile. So B, E, and G have the greatest launch speed, so they have the greatest horizontal speed at the top, then A, F, and H, and then C and D. And I think I'm going to have to stop now. So take a look at these as well.